Hello guys, welcome to my YouTube channel. So today we are going to discuss one of the most important culture systems in bioprocess engineering, which is fed batch culture. So what happens in fed batch culture? In fed batch culture, nutrients are added continuously or semi-continuously while effluent is removed discontinuously. What does it mean? On the right hand side, as you can see, at the start of the process in the fed batch culture, you add nutrients with a specific flow rate F and initial substrate concentration S naught. Okay, so after 2 hours you again add nutrients, after 3 hours you again add nutrients and the substrate. So you keep continuous addition, okay, or semi-continuous addition of the nutrients and the feed at a specific flow rate and at a specific initial substrate concentration is not, but the products are only removed at the end of the process. Okay, so that is the basic difference between fed batch culture and continuous culture. In continuous culture, the products are removed simultaneously as the substrate is fed into the reactor. But in fed batch culture, what happens? Substrate is fed after a specific time interval continuously or semi-continuously, while product is removed only after the end of the process. So as you can see on the right hand side of the figure, you add the substrate continuously or semi-continuously, while after the culture is over you harvest all the product, not before or not during the process. So fed batch culture is basically used to overcome substrate inhibition or catabolite repression by intermittent addition of substrate. Why? Because suppose you are using a culture which is very prone to substrate inhibition. Okay, so that culture stops growing if you have a lot of substrate, or that culture stops growing, that means that culture is prone to substrate inhibition. So what happens if you add the substrate continuously at after a specific time interval, the culture will stop. But if you add intermittent substrate, what will happen? Suppose you add 2 grams of substrate, 2 grams per liter of substrate, then that will be used to grow the cells. Again you add 2 grams of substrate, so it will be used in small intervals, so the substrate inhibition will not have that much of effect. So if substrate is inhibitory, intermittent addition of substrate improves the productivity of the fermentation by maintaining substrate concentration low. So if you add slowly in after a specific time interval in batches, okay, if you add the substrate in batches slowly, so what will happen? The substrate concentration will not reach a high value, it will be always in low value, and so the fed batch culture can operate in cases where the culture is sensitive to substrate inhibition. So fed batch operation is also called semi-continuous system or variable volume continuous culture. Why? Because you are adding substrate semi-continuously, and because you are changing the volume, so this is also called as variable volume continuous culture. Note, in fed batch culture the volume changes. So let us see kinetics of fed batch culture. So consider a batch culture where the concentration of biomass at a certain time is given by this expression. So x is equal to x naught plus y excess m into s naught minus x, where x is the final biomass concentration, x naught is the initial biomass concentration which you give at the start of the process, y-axis is the yield coefficient of the biomass with respect to the substrate, s naught is the initial substrate concentration, s naught as the final substrate concentration after a time say t. Okay, so now the total biomass concentration is given by xt is volume of the fed batch culture multiplied by the biomass concentration. Why? Because the total biomass concentration xt, its unit should be in say grams. Okay, its unit should be in grams, and the unit of biomass concentration, say it is grams per liter. Okay, so if you have to multiply it with the volume of the fed batch culture, which should be say in liter, to get the total biomass, total amount of biomass. Okay, so this is we are talking about, when we are talking about total amount of biomass xt, it is actually the mass of the, we are talking about the mass or the weight. Okay, not concentration. So mass is concentration, this is the, this x is means concentration, so concentration multiplied by the volume. So consider a nutrient feed is started at a flow rate F, then the rate of increase in culture volume is given by dBdt. So suppose on the right hand side you can see you are feeding the substrate at a nutrient feed at a feed rate of F. So this will result in increase or decrease or change in volume, right? So the change in volume is given by the flow rate. So dBdt is equal to F. So we can integrate this expression. So dV will be f dt. So suppose we integrate this between 0 to t, and here we integrate it between 0 to v. So at time t equal to 0 the volume is 0, and time t equal to t the volume is v. Okay, let's consider the initial volume to be v0. So at time t equal to 0 the initial volume is v0, and after time t the final volume is v. So if you integrate this expression you will get v is equal to v0 plus ft. Okay, so this is the relationship between the initial volume and the final volume along with the flow rate. So many a times in fed batch culture problems you are given the initial volume, you are given the flow rate, and you are asked to find out the final volume after a specific time interval. So you will use this equation. Now we have already talked about that the total amount of biomass, okay, which is in grams say, is given by the concentration multiplied by the volume of the fed batch culture. This we have already seen. The biomass concentration in the vessel at a time t is x is equal to xt by v. So we are doing nothing but we are transposing this thing. Okay, we are writing it from this expression only. Then the rate of change of biomass concentration is given by this thing. So this expression we have seen. So we are just differentiating this expression with respect to time. Okay, we are applying the u by v rule of differentiation. Okay, so dx dt is equal to v into dx t by dt minus xt into dv by dt whole divided by v square. Note here, this x is the biomass concentration and this xt, okay, so this xt is actually what? This is the total amount of biomass. So these two are different. That is why you have two different sorts of two different symbols have been used. This x means biomass concentration, and xt, x superscript t means this is the total amount of biomass. So by this applying distributive law, as you can see, we can write it in this form: dx dt is equal to v into dxt by dt whole divided by v square minus xt by v into dv by dt whole divided by v. So this v and v will cancel from here, and this xt by v, what is this xt by v? This is nothing but the biomass concentration. Okay, just see here, this thing only. Okay, and this dBdt, what is this dBdt? We have already seen this is nothing but the flow rate. So what will be the expression? If we, and one more thing, dx dt, this we have already seen in our previous lectures. This is what dx dt is actually what? Mu net into xt in exponential phase. Okay, this we have already seen in our previous lectures. So if we substitute all these values, we get dx dt is equal to mu net minus d whole into x. Okay, why whole into x? This here is, you can see, you are getting xt by v. Here one v is left, so xt by v is what? Capital X that you are getting. So it will be capital X. Okay, and here f by v, f by v means what? Is the dilution rate d. So simply it can be written from this expression only. If you substitute all the values here, you will get this expression. So dx dt is mu net minus d whole into x. So this expression we have derived. Now we will consider one thing. So suppose when the substrate is totally consumed, okay, totally consumed during the culture, okay, so suppose the final substrate concentration is nearly equal to 0, and x is equal to xm, which is the maximum substrate biomass concentration, is equal to ym excess into s0. Okay, so what happens? We have seen that the expression for biomass is given by this thing: x is equal to x0 plus y excess into x naught minus x. S naught minus S. Okay, this was our expression we have already seen. Now we are taking this S to be 0, and now what happens, we are also considering one more thing, that initial biomass concentration is also negligible. Initial biomass concentration is also negligible, because when we are considering maximum biomass concentration, so the maximum biomass concentration within the reactor should be much higher than what you had before or at the start of the process. So x0 is negligible. So what happens, this is x is equal to y excess into S0. So this means that the entire substrate has been utilized to produce biomass. And when can it happen? It can only happen when there is maximum biomass production or maximum biomass concentration, which is Xm. Okay, so furthermore, we operate it at steady state. So this steady state in case of fed batch culture is called quasi steady state, in which nearly all the substrate in a unit volume is consumed. And then at steady state, because there should be no change in the biomass concentration, so dx dt should be equal to 0, because that is the condition of steady state. Nothing changes in steady state. So at dx dt equal to 0, what happens? Mu net is equal to d. From this expression, if dx dt becomes 0, then from here only we can write it as mu net is equal to d. So here we have to take an important assumption that x is not equal to 0. Okay, this we have to consider. Now from monod kinetics, we know mu net is equal to mu m into s by ks plus s. So if we substitute, we get the expression for s. S is equal to ks into d by mu m minus d. So many a times what happens, you are given the dilution rate, you are given ks, which is the monod kinetic constant, you are given the maximum specific growth rate, you are asked to find out the substrate concentration, then you will use this expression. Or sometimes what they do not give directly the flow rate, they give instead the dilution rate, they give instead the flow rate and the volume. So then you have to find out first the dilution rate, which is f by v, and then ks will be given, maximum specific growth rate will be given. You have to substitute in this expression and find out s. So now we will see in the case, this we have seen in case of biomass. For now we will see for substrate. So if we use mass balance for substrate, dst dt is equal to fs naught minus mu net into xt by ym xs. Okay, so st here means total substrate concentration. This is also total amount of substrate. S superfix, so superscript t means total amount of substrate, which is in say gram, which is the unit of mass, say gram. And S0 is the initial substrate concentration, which is say in grams per liter. It is in concentration. Mu net is the net specific growth rate. Xt is again the total amount of biomass, which has a unit of mass, say gram here. And y-axis is the yield coefficient of the biomass with respect to the substrate. Now, one thing you can ask me here, that how can you write this expression? How did you write this relationship? This is from the original master equation of mass balance. I will show you. Here we know from mass balance, accumulation is equal to input minus output plus generation minus consumption. So in case of substrate, we consider that there is only input, and output means entire substrate has been utilized. So output should be 0, and there is no generation of substrate. So generation should also be 0. So the master equation of mass balance becomes accumulation is equal to input minus consumption. So input is fs naught. Fs naught. Why fs naught? What is the, we are doing mass balance. Okay. So what is the unit of S naught? It is grams per liter. Unit of S naught is grams per liter. And what is the unit of flow rate? It is liter per second. So if you multiply this to, what will happen? Liter will be cancelled, and you will get grams per second. So which is the mass balance, which is the unit of mass per second. Okay, here what is the unit left hand side? dst dt, grams per second or grams per unit time. Okay, So you get Fs naught. And consumption, for consumption we have anything which is consumed is given by minus ds dt. Okay, here we are considering substrate, so it is ds dt, and minus because it is consumed. So now we know from the original definition of yield coefficient, y-axis is given as x minus x naught by s naught minus s. We can write it as del x by del s. So if we write it in terms of differential expression with respect to time, dx by dt whole divided by ds by dt. Okay, so we can write it as dx by dt is equal to y-axis into ds by dt, and again we know dx by dt is actually what, mu net into x. This we have already seen during our videos on batch culture. So we can substitute this expression in place of consumption. Okay, so if we write it in terms of ds by dt, it will be mu net x whole divided by y x by s. So this is what we have written. Okay, so now let us see our next equations, how we are going to write any relationships between them. So St is the total amount of rate limiting substrate, and S naught is the initial substrate concentration in the feed stream. So at quasi steady state, this we have already seen xt, total amount of biomass is given by volume of the fed batch culture multiplied by the maximum biomass concentration. Why? Because xt previously, if you remember, was what, v into x. V is the volume of the fed batch culture and x is the initial biomass concentration. But in quasi steady state, what have we assumed? We have assumed x to be equal to xm, so it becomes v into xm. Okay, so here this equation, and again at quasi steady state what will happen, no change in substrate, so dst dt will be equal to 0. So from this equation only we can write it as f s naught is equal to mu net into xt by y xs m. So at quasi steady state with s is equal to 0, we get dxt by dt is equal to xm into dv by dt into x. So dv by dt is what? It is actually the flow rate. So xm into f, and xm is actually what? Y xs into s naught and multiplied by the flow rate. Okay, this we get it. Now if we integrate this expression, we get xt is equal to xt naught plus f y xs m s naught into t. So this is very important. Here on the left hand side, this is the final amount of biomass xt is equal to initial amount of biomass xt naught plus flow rate multiplied by the yield coefficient multiplied by the initial substrate concentration and multiplied by the time. So people here on problems on fed batch culture, what they do is they give you the flow rate, they give you the yield coefficient, they give you initial substrate concentration, they give you initial amount of biomass. Okay, and after time t they ask you to find out the final amount of biomass. You will use this expression, or what they do is they give the flow rate, they give the yield coefficient, they give the initial substrate concentration. Okay, they give you the initial biomass concentration and they give you the volume. Okay, so then how will you find? We have to first find out xt naught, which is what? X naught multiplied by the volume, and then you have to substitute in this expression. Okay, now let us see for product. So we are considering for product, we know P is equal to Y PS S naught. So how did we get this? This is from the original definition of yield coefficient with respect to substrate. This is written as YPS is P minus P naught by S naught minus S. So we are considering no product was there in the feed stream. Entire product was generated within the reactor. So this is 0. And we have also considered that the final substrate concentration is 0. That is, the entire substrate has been used to form the product. Okay, so then you will get this expression. Or if someone asks you to write in terms of potential product output, what will happen? You will just multiply both sides with the flow rate. So now if we take QP, which is the specific rate of product formation, QP, if we take this to be as constant, then we can write it as dpt dt is equal to QP into xt. What does it mean? It means the biomass, entire biomass that is generated is forming the product. Okay, suppose you are interested in getting some secondary metabolites from the bacterial cell culture. So entire bacterial cell that is growing will give you the secondary metabolites, say some antibiotic. Okay, so here note P superscript T means the total amount of product, and X superfix T superscript T means total amount of biomass. So if you substitute this expression, xt is equal to v0 plus ft into xm. This we have already seen in our previous slides. So if you substitute this, then this expression becomes this thing: dpt dt is equal to qp into xm into v0 plus ft. Now if you integrate this, you will get this expression. This is very, very important. So people give you problems on fed batch culture and ask you to find out the product after time t. So pt, which is the final amount of product, is given by initial amount of product plus qp, which is the specific rate of product formation, multiplied by the maximum biomass concentration. This is concentration, okay, into initial volume plus flow rate into time by 2 whole multiplied by the time. Okay, this is very important. Now suppose the people want you the final product concentration. So what we know, how to get product concentration? So this is actually what? PT, the final amount of product, is actually what? P0, P into V, and the initial amount of product is given as PT naught is equal to P naught into V. Okay, so if we write it in terms of P will be what? PT by V. Okay, so and PT naught is what? P naught. So if we substitute these values, here, you will get this expression: P is equal to P0 into V0 plus V by V plus QP into XM into V0 by V plus DT by 2 into T. Okay, D is actually F by V. So these two expressions are very, very useful for calculating product. If someone asks you to calculate the final amount of product, you will use the first equation. If someone asks you to use calculate the final concentration of product, you will use the second equation. In the subsequent lectures, we will see more on types of bioreactors.